And finally, number 10. Number 10 is about how many generators are there in a cyclic group of prime order. So let's start with a prime. So let's start with, let's say, for example, I think it's best to work in examples and then let your brain make the generalization by itself. So let's say, for example, Z7, right? So we got 0, 1, 2, 3, 4, 5, 6, and then not 7 because that's the same as 0. So which of these are generators, right? So if you take the powers of the elements, or in this case, since the operation is addition, we'd be talking about the multiples of the elements. How many of them generate the entire group? Well, let's start with this one. So the powers of 0. So first we've got 0, 0, 0, and it's all zeros, right? So no matter how many zeros we add together, it's just going to stay 0. So that is not a generator. How about 1? Well, if you keep adding 1s together, you see you eventually get the entire group. So that's a generator. How about 2s? Well, if you keep adding 2s together, you see you eventually get the entire group. And of course, I mean with the operation mod 7, you know. In fact, the same thing is true for 3s. Let's see, that would be 2, 5, 1, 4, 0. Same thing's true for 4, and the same thing's true for 5, and the same thing's true for 6. So in fact, all 6 of these elements are generators. The only one that wasn't a generator was 0. Now, compare that to, say, the 6, right? So 6 is not a prime number. And check out how this one goes. So again, 0 just generates 0, so nothing special there. Now this is a generator because you get the entire group. But check it out, 2 is not a generator because you only get the even numbers. You don't get 1, 3, or 5. So 2 generates a subgroup, but it doesn't generate the entire group. So 2 is not a generator for the whole group. And then the same thing will happen to 3, right? This would be 0, 3, and that's it. This is going to be only the even numbers again. And this is going to be, whoops, all of them. Right, so these 2 are generators, and the rest of them are not. So notice the only ones that were generators were the ones that didn't have a factor in common with 6. Right, that's how it works in general, is that if you have a common factor with the order of the group, then there's no way you can generate the whole group. The only way is if you are co-prime to the order of the group. So if you're co-prime to 6, like the numbers 1 and 5, you can do it. So back to the prime example. Well, that's the lovely thing about prime numbers is everyone's co-prime to them. Everyone less than them is co-prime to them except for 0. Right, so all of those numbers do not have a factor in common with 7, so guaranteed they all generate the entire group. So notice that in this case there were 7 minus 1 generators, right? So the full group except for the identity counts as a generator. And so to be more general, I just picked 7 out of nowhere, but in general, if it was P, then there are P minus 1 generators because there's P elements in total, and they all generate the group except for the identity. So that makes P minus 1 generators. Okay, so part 2 was let G be a cyclic group of order P. So, in other words, something with P elements. So again, I'm going to just use 7 as an example. So we've got this group G of order 7. So what's inside of G? Well, of course, it's got the identity. Right, every group has an identity. And then apparently it's cyclic, so it must have a certain generator, let's call it A. And then every other element must be a power of A, right? So we must have an A squared, an A cubed, an A to the 4, an A to the 5, an A to the 6. And check it out, that's 7 different elements. So it must be that if you go 1 more, it must be that you wrap back around. So there you go. So that's a group of order 7, a cyclic group of order 7. And indeed, if 7 is arbitrary, if it was any prime, it would look something like that. So again, we have the question of, how many of those elements are generators. And so you could go through the same reasoning as with Z7 and try and write out the powers of each element and check to see that it hits each one. But there's actually another way, which I think is better, which is to recognize that these two groups are actually isomorphic, right? You can literally just do this. Just match them up like that. And so to be a little more formal, I could say phi is an isomorphism from Z7 to G, which does the following. It takes in a number in Z7 and it turns it into that power of A, right? So it takes 0 and turns it into A to the 0, which is E. It takes 4 and turns it into A to the 4, etc. That's an isomorphism, right? Because, well, I'll leave you to check that yourself. But these two groups are actually the same. So and then here's the beauty of isomorphism is that then you can forget all the nitty-gritty details of what group you're talking about. You just know it's isomorphic to the group that you already were talking about. So anything that we said about Z7 is instantly true for G. So I know Z7 has 6 generators, so definitely G has got to have 6 generators, no questions asked. And still, just because this was the non-generator and these were all generators, well, it's exactly the same situation in G. Has to be because they're isomorphic. So G, if G is of order 7, it has 6 generators, and to be fully general, if G is of order P, then it has P minus 1 generators. And your justification can be simply that G is isomorphic to ZP, right? And that's a useful fact. Any cyclic group is isomorphic to every other cyclic group of the same order. So cyclic group of order 16 is the same as Z16. So in my opinion, it's best to, whenever you're thinking about cyclic groups, you can just transfer your thinking over to Z or Z sub whatever, because for me anyway, that's easier to think about. And so then anything you know about those, instantly true about every other cyclic group, no matter what you're talking about and no matter what your operation is. Okay, so there we go. That's number 10. Number 10 was also a pretty low scoring one, so I think I'll do a small curve on this one as well. And that's that. All right.